project, we will have a motor, and that will be connected to some sort of gearbox that you design. And coming out of this gearbox at some point will be a high strength shaft. And I was able to drill a hole in the shaft and then tie a rope or a piece of wire to it. And we'll wrap it once, possibly or twice, and then we'll suspend a mass from the rope or the wire. And we'll see how well that when this shaft rotates, it can lift the mass. Okay, so we'll do a theoretical calculation. Torque, we've heard that a lot in class this year, represents a rotational force. And the torque is going to be equal to a force times a distance. In our situation, we need to provide a force equal to the mass, is the way I should say that. So we can determine the force that's required to lift any given mass if we know what the mass of the object is. And as an example, let's just say the mass were to equal 10.0 kilograms. We're going to need to use SI units or standard international units for all of this type of calculations. So force in this case would be the weight of the mass, and weight is equal to the mass times acceleration due to gravity, or little g. So we have a 10 kilogram mass times 9.81 meters per second squared, or acceleration due to gravity. That'll give us 98.1 kilograms times meters divided by second squared. This unit, kilograms times meters over second squared, is also referred to as a newton. So 98.1 newtons. The distance, right, we just figured out the force that we need to apply to lift this. The distance that we are going to be considering is if we had our eyeball, and r in this case is 0.0050 meters. And if we multiply those two together, we'll get a value equal to 0.491 Newton meters. So again, we've just done this torque calculation. So force times distance, and we're going to plug in a value for the mass of 10, and we'll convert that mass to a weight by multiplying that by acceleration due to gravity. And then we can just swap the unit Newton in for kilograms times meters over second squared. And then we're going to multiply it by the radius of the shaft in meters. And therefore, we know that we'll need 0.491 Newton meters of torque force to lift our mass. All right, so we figured out that to lift up this 10 kilogram object, we would need 0.491 Newton meters of force. A standard VEX V5 motor that you're all familiar with working with has a torque stall value, torque stall, equal to 1.05 Newton meters. So in other words, if I just put a shaft directly into a regular V5 motor with no gearing, it should have plenty of torque to lift that 10 kilogram mass and wrap like a wire or string around the shaft. So the next assignment that you're being tasked with is for you to create in Onshape a system that can pick up as heavy a mass as you can with one motor. I took a stab at this, so I'll show you what I did, and then I'm curious to see what you could come up with. So I set my motor to a gearbox where I have, yes, it's a 36 tooth gear, and there's another shaft nearby that goes to an 84 tooth gear. And on this shaft, there's another 36 tooth gear here, which goes to another shaft, as you might expect, with another 84 tooth gear. So I went 36 to 84, 36 to 84. Okay, so here's our picture. And if we're solving for our gear relation, which we'll just call GR going forward, it's going to be the product of the driven gears divided by the product of the driver gears. In our case, this would be a driver, and this is a driven, and then this is a driver, and that's a driven. So hopefully that makes sense. The one that's spinning the other one is the driver, and the one that's being spun is the driven. And again, sorry, that's an R. This isn't. Okay, so if we look at the driven gears, we've got two 84 teeth. So that would be 84 times 84 over the two drivers, 36 times 36. Okay, so that will give us 5.43 as our gear ratio. And our gear ratio is going to equal the torque of the output shaft, ideal, divided by the torque, way off, sorry, the torque of the input shaft, ideal. So the torque of the input we know is 1.05, and the gear relation we just figured out was 5.43. So we'll just leave this as torque output over torque input, which is 1.05 Newton meters, and we can solve for the torque output ideal, which is going to come to 5.7 Newton meters. Oops, I'm off again. Now, because we did two different interlockings of gears here, so 36 to 84 and another 36 to 84, we're going to assume we lose 10% with each one of those. So although this is the ideal amount of torque we would have on the output shaft, due to friction between the gears, we're going to lose some of that, and we're going to lose roughly 20. We'll lose roughly 20%. So we'd have 80% remaining. So we'll take that value, multiply it by 0.8 for 80%, and that will give us 4.5 Newton meters of actual output torque. Okay, so we said we'll have 4.5 Newton meters of available torque on the output shaft. And if we go back and remember this formula, that torque is going to equal force times distance. And again, our case, the distance is going to be the radius of the shaft that we're wrapping the wire around. The force will be whatever it is that we're trying to lift, and the torque is what we've already calculated. So we can plug in 4.5 Newton meters of output torque. And we really want to solve for, well, what can we actually lift up if we're wrapping it around a shaft that has a diameter of 0.0, I'm sorry, radius of 0.050 meters. Well, if we do this, force equals 4.5 divided by this, and therefore the force we should be able to lift is going to be 900 newtons. And again, if we want to convert that to a mass, we remember that weight, which is our value in newtons here, equals mass kilograms times acceleration due to gravity, 9.8 meters per second squared. So 900 equals the mass in kilograms times 9.81 meters per second squared. This is 900 newtons. So the mass in kilograms that we can lift is therefore equal to 900 divided by 9.8, or 91.7 kilograms, which is quite a bit. And if you multiply that by 2.2, which is how many pounds are in a kilogram, you'll get to 201.8 pounds. So the system we've created should be able to lift up maximum 201.8 pounds. And here you can see the setup we're using, with the 36 going to an 84 and another 36 going to an 84. And here's the 70-pound dumbbell that we've attached to the apparatus, and I'm now running the motor, and hopefully you can see that the 70-pound dumbbell is slowly starting to get picked up. And it's still touching the ground, but at a certain point we should clearly see that it is now off the ground. I think you can see it swinging, and now you can, I think, clearly see it still going up, and the motor has fully lifted it.